Okay, now as we continue the second part of the sources of error. So the last the 5 type of error we already discussed, all right, the last week, and we're going to continue with that today with that roundup of error. All right, we're going to discuss anyway that, and then we're going to discuss about the truncation error. Okay, what does it mean, the truncation error, and when it is happened and when it's occurred usually, and how do we need to calculate on that. And then the modeling error, instrumental error, and machine error, as well as the human error. Okay, so instrumental error or machine error. Okay, all right. Now I'll tell you what, that modeling error first. Modeling error usually actually it's not usually not in your syllabus. However, we need to consider because most of the numerical method will be imposed on the modeling. Okay, the models mathematic. So in order to calculate that or predict that the solution. So basically the modeling error is occurred when say in that when you are developing a mathematical model. Okay, so even though it's not a part of our syllabus, but I'll just give you some brief introduction. How does it works? Say, for example, you are developing a model for the tsunami model, like tsunami, right? Tsunami models. Okay. So most of the researchers, they use the Navier-Stokes model, all right, Navier-Stokes model, in order to develop the tsunami model. But remember that you cannot use the basic Navier model because the lack of the informations. Okay, there is a lack of information in the basic model, which is the Navier-Stokes. They considers only very few parameters. Okay, the few elements in the basic Navier-Stokes model. But when you decided to use the Navier-Stokes model in the tsunami to develop a tsunami model, so what will happen? You have to consider the other elements as well. So, for example, in tsunami, it is definitely there is a magnetic wave since it's a salt water. Okay, it is salt water. The other elements is there will be the magnetic fields. So you have to consider the magnetic field elements in it. So you need to add on in that the Navier-Stokes model. Beside that, always remember in the sea wave there is a turbulence. Okay, the turbulence flow. So turbulence flow is also like one of that is a crucial in that the sea water modeling. So that part you need to add on the Navier-Stokes equations. So this is some partition, the small partitions which is you have to add on in that the basic Navier-Stokes equations. All right. Sometimes the model is just missed off any of these elements. So that means the chances to the model prediction will be not that accurate or less accurate. Okay, so that is we call a modeling error. So when we develop a model, you need to consider for every elements or each parameters, which is the based on the problem you considers. Okay, so you need to add on that into that your model. Okay, otherwise your model will be inaccurate and it's not really accurate for in order to prediction. Okay, so likewise is other cases. Okay, nanofluids. Okay, even the river flow models. Okay, so everything. Okay, is a similar cases. Okay, so remember that. So that we call is a modeling error. Instrumental and machine error, we get very common in use. Like for example, like best example is a ruler. Okay, so ruler, when we just measure any of the object or any of that specimens, they give you measurements like millimeter. Okay, millimeter. But it's a vernier scale. When you use the vernier scale, or microvariance scale, they will give you more accurate, at least 2 or 3 significant places. So that is our content. So the instruments error, they will call it instrument error. Human error is very common. Okay, is we cannot avoid out of it, so it's always happen. So this is like human error is one of that the very common happen in everywhere in each of every things. So one of them is yeah, what happened last week. Okay, there's a human error as well. So that is actually the human error, which is we have to look into that when you just analyze, you must look into that the calculation, and as well as you look into that the comparison test in order to the way you done is correct. So always remember every time when you do even in an example. So when you just try to attempt any of the questions, so you may definitely do some very minor error. Okay, unless it's very concerned, very serious on that, you precisely check one by one without any distractions, so you will get the answer. But however, it's very common in it happens in any field. So the human error is one of the common happen in that each every field. So you have to look into it and you have to recalculate, and recheck is one of the essential. So when you just do that, the calculations. Okay, the human error. Okay, so since this error, the modeling error, instrument error, and human error, so it's already like very easy. So you all know that about it. Okay, the most important is that the data propagation propagation error. So this is like the we also call as a secondary error. Okay, so for information, the true error until the human error we call as a primary error. Okay, so which is straight directly we can see that the errors. The data propagation error is we call as a secondary error, because the data propagation error is a cause due to the primary error. So we call as a propagation error. So it's what we're going to discuss today, the 3 error. So first we start with the round off error. Okay, what those we call as the round off error, and when it is happened, and how we're going to determine those values. Okay, usually it's caused by representing the number approximately. Okay, for example, say if it is 1/3, so if you just convert into the decimal numbers, so it's a 0.3333. So see that it's a 6 significant places or 6 decimal places. All right, but these are not as accurate, but since we just only show in the 6 decimals numbers. If you need a more accurate solution, so you need to add as many as we can. Okay, if it is 100, it's more accurate. If it's 1,000, it's even more accurate. Okay, so it depends. This is what we call round up error. When you just make the round up the error, so what will happen? This causes for the remaining calculation will be less accurate. Okay, that's what we just trying to explain on this. As well, the square root 2. Okay, it was root square errors. So when the root square error, so for example, you square root the 2, so you get a 1.142. You just leave it as it is in this point. So 4 decimal numbers. So that means it's not that the exact solution is. So if you by adding that the number of terms at the back, so that will be more accurate compared to that 4 decimal numbers or 4 decimal places. Okay, so see that this if this value, if you implement it or you just carry out for the further calculation for the remaining calculation in order to get the final solution, so definitely the final answer will be inaccurate. Okay, compared to we just give that like 10 decimal numbers or decimal places. Okay, why the round off error is important? Okay, now it's also like happen in our real life applications. It is one of them. All right. So if you can see that there is a video, probably you might not the sound. All right. still work on that, but just you don't really need sound out of it. So just okay. So what do you get out of these videos? Does anyone can tell me? Anybody want to try? Hangzi, no?
Yes, doctor.
Okay, so what you can conclude of this video?
One bomb failed to shoot.
Okay, so there's some inaccurate. Just an example. Thank you, Ang. All right, thank you. Okay, this is just an example. Just one of that video. They said that the inaccurate maybe your measurement or computer settings when you just launch a rocket. Okay, all right now. So if you can see the real life application, all right. So the a time that is 28 Americans were killed on February 25th in 1991, okay, by an Iraq Scud missile in Dhahran, Saudi Arabia. So this is one of that incident is famous and is considers is like the best example and is a famous anyway in a numerical field. So it which is causes of the round of error by the computer. Okay, the computers make some arithmetic mistakes on, I mean, it's not a make an arithmetic mistake. I mean, the computer is just only contain of very last bit in order to compute the solutions. Okay, all right. So the Patriot defense system failed to track and intercept the Scud. Why? Okay, this why is because if you can see that the clock cycle for the 1 per 10 seconds, so it just only represented in 24-bit fixed point in the normal computer. The back in the time, so we have the computer bit is just 24. I mean, I'm talking about 1991. So now we have a 64, right? Our computers bit is like 64. All right. So back in the time in 1991, it just imagine it's just only 24 bit. Okay. So which means when the missile is launched, all right. So it's not really captured for accurately. Okay, when the radar will capture signals, so it's not really that accurate. Okay, because the computer capacity just only 24 bit. So now another problem is the battery was on that 100 consecutive hours. That means it's too heated up. Okay, so that is one of the another reason, which is the inaccuracies in the calculations. All right. So this is the calculation, and they found that the accuracies, the inaccuracies are about like 0.342 seconds. So that the two measurement is causes due to that the missile is launched with recorded was late. Okay. Now the reason is what happened. The shift calculated in the ranging system of the missile was 600 87 meters. So which means is expecting is less than that. So which means, like for example, if it 687 meters means, say I just give you an example. So the best lesser is a possible. So each every 10, so for example, each every like 100 meter, for example, the scat in the radar, it will be captured that the to locate that the missile. Okay, but in this case, the radar is capture the pictures is a 687 meters, and they come one, the first signal. The second signal, and every 667 meter, they go for the second signals. So that means the timer, the second is higher. So what happened? The distance is become even higher. So that means there's an inaccurate calculation in that due to the problems. So what happened? The target is considered to be out of range when they're supposed to be hit, but the missile is hit in the camp of the American soldiers. Everyone was dies. Okay, so this is like one of that very important why that the round-off error is important. So when you calculate the measurement in the computers, it has to be accurate. All right, now look at that this problem. This is that the contractions problems in order to determine that the diameters. Okay, now we look at that the effect of carrying significant digit in the calculations. Okay, in the contraction in the diameter. So this is that the given formula. Let me just use my PowerPoint and laser point. Okay, so this is the given the equation of the contractions. Okay, so in the given in the integral equation form, integral forms. So D stand for the diameter and the alpha. Okay, the alpha is a subject to you need to determine, and the T is a stand for the temperature. Okay, and all the information is given. Okay, the information is already given. So D is given is 12.363, and the lower boundary, the upper boundary TC is given as minus 108 degrees Fahrenheit, and then the TA is a lower boundary, which is the 80 degree Fahrenheit. Okay, and this is the value expected value when you integrate the functions. So this is that the value has to be. Okay, now as you can see that each every that the observed point. Okay, so this is that the value is if you use the base on that the observed point. So corresponding values, like for example, like say 220. So if a minus 220, so if you just use that equation and you get that the alpha value is a 4.08. So that will be here. Okay, this alpha value. So 220 somewhere here. So this value will be 4.08. Okay, likewise the remaining. So this all the observed value based on that the given the value, and these are corresponding value after when you substitute those value into that the integral equations or the function after once you integrated. Okay, now same things when we try to generate the function using an Excel. Okay, when the Excel what will does, okay, the Excel will be compute based on that the some error terms. So if you just not consider that decimal numbers, they just only they give you straight away use that the minus 1 times 10 power of minus 5. And the second terms, they just t square, and then the second terms they given 0.062, and then they give you two significant places, and that this is your your parameters. Okay, the unknown parameters that already they determined for you. But the most important is these two things. So this is the roundup, and they give you only the least significant places. So that it will be causes that error terms. Okay. Now let me see that how it happens. Okay. So now we just upload that the observed and predicted value. So observed value, this is that the given observed value. Okay. But the predicted value based on that the Excel regression data. So they give you the 2.76 by using this formula. Okay. These are generated from that the Excels. Okay. So they give you that 2.76 compared to that your observed value for each every temperature the given according to that our that we will set in that in order to develop the tables. Okay. Now, so if in the regression data, if you just give in the scientific format, which is we consider that the number of significant error, say we just add the significant error in the significant terms, all right, in that the each every terms like t square. Okay, this is supposed to be t square, guys. Okay, so minus 1.2360. So this like just now we see that just only minus 1.10 power of minus 5, 10 power of minus 5. But now we add on the some significant error like a 4 decimal numbers. So 1.2360 exponent 10 power of 5. So this is like 10 power of minus 5 t square. Likewise, we just add on the 4 decimal places, which is 6.2714 10 power of minus 3. Okay. And then so we can substitute the value again, all that observed value, the corresponding the t value, we substitute into this function, and we get that more accurate solution as follows. Okay. Right. So after one, we just add on the significant numbers in the equation, and you can see that the predicted value is moreover similar to that the observed value or the given value. Okay. So this is based on your equation. We just use that the exact value standard integration. Okay. And then we substitute the value and the outcome. And this is the predicted value based on the Excel. After once we just corrected according to the scientific format, which is we add on that the significant numbers. So this value is pretty much closer to that the observed value. Okay. So now predicted value now 2.46 is somehow is closer to that the observed value. Okay. Sometimes it's less, but however, if you compare to the previous one, is even closer to that observed value. Is it clear, guys? This part? Any question? Hello?
No question.
Is it clear?
Yeah, it's clear.
How about the others? It seems like the class is dead silence. No one asks any questions. No even sounds, no any response. Are you there, guys? Or sleeping? Okay.
Yes, I think it's clear.
Later, I'll give a quiz. All right. I'll just do anything spontaneously. Just make sure you're there. It's okay. Okay. All right. Now, so this is a you can see that the sum of the value we wrap up everything and we see that the observed value and the value once we make the predictions after the corrected version, and then the value which is before that make the corrections based on regression data from that Excel. Okay, so if you can see that you can see which one is more closer, whether the corrected version based on the significant numbers, or that the standard one from that the Excel. Okay, so it's a very far difference compared to that observed value for each every corresponding to that the temperature. Okay, so this is more accurate to that the observed value. Okay, so you from here you can easily can see that how important the roundup error is. Propagation error. All right. So when you just look into that, the any of a approximation, okay, there will be some additional terms. Okay, I'm pretty sure you're familiar the Taylor series equation. I've been seen before. Okay, even you are in the secondary school. All right, the Taylor series. Say if any of function, for example, like Maclaurin series. Okay, Maclaurin series is derived from the based on the Taylor series. All right, say if it is fx, say they represent an approximation. So this is a the number of terms by differentiating that the function with that the small approximation for each every nearest terms. Okay, for example, a function fx can be differentiable for n+1 times in the interval between the 2 points which is given. Okay, so based on the given interval, so you can able to determine that the terms, right? So as much the truncation, I mean the term is increase more and more. So the solution you obtain here, it will be more precisely to that the exact one. Okay, for in the numerical method, so we don't have to look into that each every terms. Okay, we only need to consider a few desirable terms which is closer to that the exact solution. Okay, so for example, fa, so the function when you substitute with the a, so which means these are first terms, and then you differentiate the function and you substitute the a, and then the x minus a. So this will be, there will be the linear system, so it will be closer to the function. Okay, so which mean I can show you that some illustration for your better understanding. Say this is your graph. It's a pen. Okay, say for example, so this is your graph. Just assume that is your graph. Okay, and this is your fx function. Okay, this is your original function fx. Okay, so if it is fa, so that's going to be the straight line for any point here. Say if we just only consider just only the first terms. Okay, we just only consider the first terms. All right, say first terms, so that could be just only one dot here. They show only point, they never bring any information, or maybe a straight line. Okay, so a straight line, it don't give any particular information out of it. So when you consider second terms, this is a linear function. So the linear function is just maybe it just could be the straight line. Okay, I'll try to use the different colors so that you can see that. Just a straight line. Okay, just straight line. So when you consider the quadratic terms, all right, the third one. Okay, so this is a second, this is a third. So that will be slightly is going to be like this. If you consider the term 3. Let me choose different colors. It just slightly, but it touched the point and then it go up like this. Okay, so as much the term is go further, add on the terms, So this will be, it come closer to that your actual function. Okay, so that is what we, the term is importance. Okay, so the trunk, what happened when we discarding, or we discard the remaining terms, all right, that we just consider only the few terms here, and you compare with the exact solution, that what we call the truncating or truncation error. Okay, is that clear, guys? Is that clear?
Yes.
Any question? How about the others? Hello? Anybody home?
No, Pastor.
Okay, now look at this example too. Okay. Okay, the Taylor series approximating that into x, the exponential functions at the point when a equal to 0 is given by this function, which is e exponent x equal to 1 plus x plus, you still need to use the same Taylor series formula, but this is 1, 2, 3, 4, 5. These are 5 terms there. Okay, so what happened? We just only look at the first 3 terms. Okay, say in order to determine that the truncation error, so you can find easily that the difference by subtracting the accumulation of the first 3 terms with the exact solution, then you get the truncation error. Okay, so take the actual value, the exact value, the function, and then you subtract the first 3 terms of this. All right, and then you can find that the how many the figures is a difference from that the actuals. So that we call as a truncation error. Okay, if you add more, then the error will be reduced, and you add more and it will be further reduced. Okay. Okay. So in numerical analysis, this is like also this is very important. You need to consider, because, for example, in a finite difference, standard finite difference, we have a forward finite difference, we have a backward finite difference, and we have the central different finite difference. If you can see that the forward and backward finite difference formula is actually it's a low order accuracy. Okay, if you compare to the central different formula, because it's a will be high order accuracy, because they consider is a high order second order accuracy terms. And then the forward and the backward finite difference formula, it's actually called as the first order accuracy formulas. Okay, so even there are a lot of research still ongoing. Okay, it's also like a part of my research works as well. So some of my master students, they done that recently. They done compact finite difference scheme in order to approximate that the nonlinear ordinary differential equations, and they compare with the result with that the standard finite difference. Okay, and from that you can easily can be seen that the how much it's the truncation error is. Okay, the error you got a value in that compared to the exact solution. So that is a one of that the ongoing research. Okay, so also remember that this also can be improved by adopting by other schemes, and you put in together with that the finite difference formulas. Okay, so later when you just go for your final year project, or when you just conduct that master, so I will give you more examples out of it. So there is actually a lot. It's Gauss, Gauss quadrator, there is a Romberg, there is a Boole method, there's Simpson 1 per third, Simpson 308, okay, trapezoidal methods, All right. So that's every mostly that type of you can add on the terms in order to get more accurate solutions. Okay. Now, example 2, look at the example 2. So we're going to determine that the absolute error absolute relative error or absolute relative approximate error. So we can easily calculate, if you can see that by using the same problems, the one we used before. So now we're going to determine that the absolute relative error. Okay. So the n is stand for that the number of terms. Okay, terms 1, terms 2, terms 3, and term 6, and so on. So, okay, the n, and then the exponent 1 per 2 is that the exact value. So we just get that the value from there. Okay, in the given function, and then this is an approximation value. So I think I already taught you before, right? So you can use that approximate value. So now you're just going to determine that the exact value and corresponding that approximate value. Okay. So now we're going to determine that the percentage error, how much the difference errors or the absolute relative errors are occurred for each every terms. So if the first term you're unable to determine that the terms, unable to determine that the absolute error. Okay, for second term onward, yes, you'll be able to find that the terms. So what all you need to do, you just take that the approximate error divided by 2.2, which is the exact value, and you multiply by 100, you get that the percentage error, how much the error is. And you can see that the n is increases, okay, the terms increases. So the accuracy, the what do you call, the error is, the percentage error is reduced. Then the accuracy is improve. Okay, so the first terms, okay, in the when n equal to 2, so you got a 54.5% error. And then when at the point when n equal to 3, you get 24.65 absolute error. And then when the term is just increased and then you reduce until you just when the term is when it's n is n 6, so you get that the absolute error is just only 0.62500. That means this is more accurate. I mean, as the term is increases. So this is the best practice I can show you to just how the accuracy is improved as that the term is increased. Okay, and you can easily determine by using that absolute relative approximation error. So maybe I just gonna ask one of these questions in your test. All right, just be prepared for it anyway. So I think I haven't done that before, so probably there could be one. Okay. Okay. It's still a truncation error, all right, and we just use that the forward difference formula. All right, we're going to calculate that determine the area under the curve. All right, so usually that the forward difference formula is represents, we can derive from that the function. So this is your given function. The curve here is fx function. Okay, and the formula is derived by the first order. You differentiate the function, which is f x plus, and this is the lambda. This is delta x. The delta x is the step size, the difference between the 2 point P and Q. So if you take point P minus the Q and you calculate the distance, okay, the step size, and then you subtract that original function and divided by the step size or the distance of the step size, and you will get that the approximation value. Okay, all right, so just give you that example so that you can see that better clear picture. So look at the example 3. They require to just to determine that the function when the x equal to 3 for the given function, which is fx equal to x square, by using that forward difference formula. So which is the given this, and the given the step size. So is a delta x is equal to 0.2. Some books they refer to h. Okay, so some books they refer to delta x and so on. So okay, so what does it mean, this delta? The delta is means you just read as the changes in x. Say this is your x1, this is x2. So if you see that delta x means the changes, which mean the difference between the 2 points. So p minus q, and they will give you that the how much the difference is, the step size between the 2 points. Okay. All right. Now, so in order to determine when the x is 3, so you just plug those value into the forward difference formula. So 3 is a given value x, and then this is a step size which is 0.2. All right, and minus your fx value when you substitute the 3. So you get the value which when you just plug the given quadratic function into it. So you get the value is 6. Okay, so now the exact value is you can directly differentiate this function, which is 2x, and you substitute the 3 and you will get the 6. Okay, and this is your approximate value. Okay, when you just plug in those value and you can see the difference. So how much the function is, calculate yourself. Okay, 3.2 square minus 3 square over 0.2. So that will be your approximate value, and then you need to check with that your exact solution. Okay, so this will be healed. This value will be 6.2. So the truncation error, so will be you take that your approximation, your exact value, you subtract with that your approximation value. So you get that minus minus 0.2. So that is your approximation error based on your the result from that your approximation value from that the forward difference formula compared to the exact value. Okay. Okay. Now, can you find that the truncation error? So if they say that the step size now is a 0.1, can you do it? Can you do it quickly? I just give you 1 minute. And let me know the answer. You can use the chat box as well, guys. Okay. Afiq got minus 0.1. Who else? Okay, Nurul get minus 0.1 as well. Okay. All right. So that means most of you know how to do it now. Okay. Glad to know that. Okay. Thank you, guys. Thank you. So now this how it has to be. We're going to calculate the truncation error. Okay. So when I just give there some examples, so questions, you know how to determine the truncation error. Okay. Now we're going to use that the rectangle to approximate that integral. Okay. All right. Say example 4. I just throw out a lot of examples so that you be familiar with those type of examples. Okay, those are problems, and that could be you use as a guideline to just you use that the other problems. Okay. Okay. So now they give you the two use the two rectangular equal width to approximate that area under the curve, the given function for the fx equal to x square for the interval 3 to 9 and find that the truncation error. Okay. So now, as you can see that they give you the two rectangular square, okay, rectangular two rectangular in order to determine that the area under the curve, okay, and there is a three width 1, 2, 3, okay. So and they given the function, the original function, which is y equal to x square, this is a quadratic function, okay. So now you need to determine that area under the curve between 3 and 9. Okay. So in order to see the distance here, it's very easy. So you just plug the 3 into that function. You get that the y is 9 here at this point. So all over until this point is a 9. And then when you substitute the 6 into that function, you get as a 36. Okay. You get the y will be the 36. Okay. Now, so you can use that the step size. The step size is a constant, which is 6 minus 3. You get a 3, and 9 minus 6, you get a 3 as well. So 6 times 3, you get a 18, and this is 36 times 3, you get 108. So yeah, and then you add up these two, you get that the area under the curve. But you need to compare. This is like based on the rectangular. This is what we're going to do now. So first you need to choose that the difference between that the okay, so 3 and this is 6. 9 times 3 is 27. Sorry, 27. All right, and this is like you get 108. Okay, so add them these two, and you get that the total value. Okay, so first this, you just 6 minus 3 at the point, the width is a x is 3, so you get the width is 3, and you substitute into that the given function, so you get a 27. And then for the second rectangular, so same things you need to do, and you get 108, and add up these two, you get a 135. Okay, these are area under the curve. Okay, now you need to compare with that the exact solution. As we know the exact solution, we got the 234. That means the very far difference. Okay, but since this is a approximation equation, so you still able to find the solution closer to the exact solution. Okay, so what happened? So when you find that this the point, this is the space over here, the triangular space here, is all is left out. It's not not into the calculation. So that means these are all the error terms. So which is a miss from that the calculation. That means it's considered these are all the error regions. Okay, we call it all the error regions in that when you just calculate that in the trapezoidal cases. I mean like rectangular cases. Okay, now. So if you see the difference, that what the difference between the truncation between the exact and the approximation is about 99. Okay, so this is the, which means you take the exact solution is 234 and minus with the approximation is 135, and the error terms is the truncation error is about 99. So how are we going to improve this? Now the question is, how are you going to improve this error? Can you tell me? Anybody? I think I ever mentioned this in the first class itself. Anybody want to try, guys? Yes, Ang?
Reduce the width.
I couldn't hear you, sorry. Hello? Hello? Lim Jia Ki.
Hello.
Yes, Lim. Can you tell me
Hello.
how you can calculate it?
Reduce the width.
Reduce the width. So what does it mean, the reduce the width? That means we need to add the rectangular.
Yes.
In other words. Okay, thank you, Lim. Good try. Okay, you can add on the rectangular terms. So by adding the rectangular terms, so that you can even get the more accurate solutions. Okay, now can you find that the truncation error with that 4 rectangulars? So what would be that the error is, the truncation error? Is it like closer to the actual value? The solution is, or less than that, the 2 rectangular. Anybody want to try?
More than. I think it's more than the 2 rectangle.
Okay, which means it's correct call. Okay, thank you. So it's closer to that the exact solution. That means the accuracy will be improved. Okay, so which means the error will be lesser. Okay, because we're adding that the terms, the rectangulars, the truncation will be less. All right, exactly. Okay. Now we just covered that the last part of that, the propagation of the error. Okay. So let's take a look on this. Okay, before I continue this, any questions about round-off error and truncation error? Any questions, you guys? You have any question to ask? Maybe I can repeat again. Is that clear? You get the broad pictures out of it?
Yes.
Okay, thank you, Ang. Okay, propagation of the error. Okay, let me see what does it means. Okay, propagation of error, as I said earlier, this is a secondary error. Okay, the error which is caused due to that the primary error. Okay, the error which is caused by the primary error. So in numerical method, you should understand that the calculations are not made with that exact numbers. This is very, very important knowledge. You have to know that we not deal with that the exact solutions. Okay, so we only look into that the approximation. So what will happen? So this inaccuracy propagate through that the calculation. So how it would be? How do this inaccuracy propagate through that calculation? So this is due to some, as I said earlier, the primary error. Okay, the primary error which is caused to the secondary error, which is the propagation error. So we see that some formulas how we should carry out in order to determine that the propagation errors. Okay, take a look at this example. Okay, find the bound for the propagations in adding two numbers. For example, you see the given x and y, and every elements which is x has their own error. Okay, which is plus minus 0.05. Which is this could be less than higher than the 1.5, which is 1.55, or this could be 1.45. Okay, so this is an individual error for the x. Likewise for the y. So y is as a one term the error which is plus minus 0.04. So which means it could be 3.44, or this could be 3.36. Okay, that's a two possible value of these numbers. Okay, now how do we need to overcome these issues in order to write the propagations error? How we need to write that? Okay, so always remember that we have to consider for every item, I mean all the items like maximum and the minimum errors of these two cases. Okay, let's we do it one by one. So how we need to solve it? Okay, first we need to find that the maximum possible value. Okay, as we know, the maximum possible value is x equal to 1.55, and then for that y is maximum possible value would be 3.44. Okay, and then we're going to determine that the value, how much that the two value. So the maximum possible value when this condition x plus y, so that could be 4.99. Okay, now next we're going to determine the minimum. Okay, so the minimum possible value, as I said earlier, this could be 1.45 for the x, and for the y, it could be 3.36. Okay, and then we need to add them up, so we get that the lower possible or the minimum possible value by adding the two elements, so x and y, it will be 4.81. Okay, therefore we can conclude that the propagation of the error we can easily can be concluded as, so this is a fall between 4.81, so which is less than equal x plus y, or less or equal than 4.99. Okay, so y you must give within this range. Sometimes this could be is the x is a 1.55, and y will be could be the lowest, which is 3.36. Okay, or vice versa. Okay, so that you have to take the maximum, the most maximum, and then the minimum value, so that we just give it within the two range. Okay, so all the whatever the outcomes, so whatever the error is, this will be fall within the two range. Okay, is that clear, guys? If it is clear, then the remaining part will be easy for you. Any question from this? Any question from this part, guys?
No question.
Okay, thank you, guys. Guys, please respond. Okay, I do not know whether you are there or not. Say that is a very simple terms when we just going to determine that propagation of an error. Okay, say what if there is on more sophisticated function, or probably a complex is involved, like some values, I mean like some formulas, okay, to determine the function. Okay, so usually we use this formula, so we call propagation of error in formula, so it will be in this form in order to determine that the error terms. So this is a delta f, which is changes in f, this equal to the partial derivative, which means this is the mean is a partial derivative f over x1, so which mean regardless any numbers, if it is x1, so we just only need to differentiate the particular elements or particular variables. So if you differentiate that x1, that means you need to multiply that the delta x1. So it just only considers only one variable for every terms. So plus, if you just look at that in the formula, if it is there is a x2, so you only differentiate that only the x2. The remaining variable will be constants. Okay, so this is the standard formula we use. We call as a propagation of error formula. Okay. Now take a look at this example. The strain in that axial member of the square cross section is given by, so this axial numbers is F is stand for that the force over h square. The h is stand for that is the distance in millimeter. All right, and then this is a E is a energy and is a evaluate in the Pascal. Okay, now the given that the force is given is 72 plus minus 0.9 Newton, and then the H given is 4 plus minus 0.1 millimeter, and then the energy is given is 70 plus minus 1 gigapascal. Okay, now as you can see here, this term is not in the international standard. Okay, this is not in the international standard. Sorry guys, thirsty. Okay, so now what all you need to do, first you need to convert those elements, the given function, the element each every one of this formula, you have to convert into that the standard forms. Okay, so for example, so usually the standard forms of the H will be in the meter, not in the millimeter. Okay, and energy will be usually in the Pascal. Okay, so you need to convert those figures first. Okay, now the idea is you need to find that maximum possible error in the measured strain. Okay, so the strain in the Excel members is given is this formula. So we're going to find that each every element. So which means you have to look for that the partial derivative respect to that the strain in the Excel members. Okay. Now we do it one by one. So now first we need to determine that the strain in Excel members value. Okay, so as we know that the formula is given here, F over H square multiplied by that energy. So as we know that the force is given is 72, and then remember you have to change it the millimeter to the meter. So this will be the millimeter is a 10 power of minus 3. So I think this is a physics. I think you may know that this is the convention from that millimeter to the standard international standard. So just add on that. And then the gigapascal, as you know, the giga is a 10 power of 9. So you just add on that gigapascal. So you get that the solution, which is 61.26 times 10 power of minus 6. Okay, so the minus 6 is actually you can round up because this is a micro. Remember the micro, how they're going to use it? Micro, it look like mu. Okay, so we change it that the micro is substitute with the 10 power of minus 6. We change it in that joule. Okay, and then this should be 4. Okay. Okay, now when I'll change it later, this guys. Okay, so then you just you make the convention because this is a Newton. Okay, and bring that the meter. Okay, up there. Okay, meter square. All right, up there, and then become is a minus 2. And the Pascal, you just bring up PA is become a P. The symbol is a PA minus 1. All just bring all up. Okay, now this is that the strain value. Okay, the strain value. So now we're going to look for that the error terms. The error term for each every element which is given in that questions. Okay, for individual, for that the force, as well the H, as well for that the energy. So now we're going to use that the propagation error formula in order to determine those value. Okay, now first of all, what you need to do. Okay, first you need to write that the formula. So which is the changes a delta, the strain function. Okay, the delta strain functions E, and then you're going to determine each every terms here. So you can easily find out. All right, by you evaluating the the function based on the given function, the strain equal to f over h square times e. So that means you're going to differentiate this function respect to f. So you get the function 1 over h square e. That means the f become a 1. So this is your partial derivative respect to f. So likewise, you're going to differentiate the second terms, which is you need to differentiate now the h. Okay, so when you differentiate the h, the partial derivative differentiate respect to h, the remaining constant will be remaining variable will be the constants. So it's become 2f over. Don't forget the minus, because the h square is you bring up become a -2. So bring in front and then in -1 it become -3, and after that you bring down it become h power of 3. So this will be become -2f over h cubed times e. So this is your partial derivative for the delta partial derivative of e respect to partial derivative respect to h. And then likewise for that, you need to find the partial derivative for that e. So when you differentiate, again, same things, you just bring that e up and then you differentiate and you bring back again, and that will be minus f over h square e square. So this is that the individual partial derivative for each every element in that the function. Okay, now, so what you're going to do, you're going to substitute in each every one of it inside. Okay, now, so one, you just look at that each every element. So you just substitute according to the function, the age and energy and the force respectively, and then you be get that the final answer, which is 5.396 micro Newton meter over meter square time Pascal. So this is that the error terms you can derive based on that given function. Okay, now, so hence the final answer that should be, you first give that the original function. Okay, so 60.4286 micro plus and the error terms, which is you derive from that the error propagation formula. Okay, so this will be your final answer. Okay, so remember that this is a very easy. So this is like every time maybe the different function will be given, different type of equation. So you have to do that the same things. First, you need to find that each every element, you do the partial derivative for each every one of it, and then you substitute into that the formula into it, and then you substitute those value in, and then you get that the error terms. What is that the error terms in that the particular function? Okay, is that clear? Any question from this part, guys?
Yes.
Clear, huh? Okay,
Yes.
thank you. Okay, next. All right. Remember that in propagation of error, you also there is we usually claim that the subtraction of numbers that are nearly equally can be created unwanted inaccuracy. Okay, so by subtracting the number which is closer to that the actual, it also lead to the unwanted inaccuracies in that function. So we can prove that based on these examples. Okay, and based on this function. Okay, say let z is x minus y, for example. Okay, so let z x minus 1. So now we use the propagation error formula. Okay, say we're going to use that propagation error formula. So we by writing that the delta z, okay, so we're going to differentiate that component x. We do the partial derivative of the component x here, okay, and then plus that do the partial derivative for the component y, So you get, if you find the differentiation, you derive that x elements, you get 1, and if you derive that y element, you get a -1. So if you substitute into that the function here, the value accordingly, and you need to put that absolute signs. Okay, so which is the delta x plus delta y, because this will be lead to error terms, which called unwanted inaccuracy. Okay, so now if these terms, if we just find that you convert into relative terms. So relative terms, which means if the terms delta z over z over, and we know the delta z over z and make equal with that the result of the delta z, so which means x minus 1. So we be able to see that the relative change is become like this. Okay, so which is delta z over z, okay, equal to delta x modulus plus modulus x delta y modulus over x minus y. So this is we call as a relative change in that the propagation of error. Okay, when the case is a subtraction, in order to determine that unwanted inaccuracy. Okay, so take a look on example. We can see the clearly pictures. How does it means? Okay, so remember this formula, and remember that there is no unit for it. Okay, since we just divided by the relative figures. Okay, take a look at this example. Say the x is given is 2 plus minus is a 0.01, and the y is given is a 2.03 plus minus 0.01. Okay, so say we carry out that the relative function, okay, the relative propagations error function. So since we can write in this form, so we can add the error terms, which is, you know, that the x relative error is 0.001, and the y the error term is a 0.001 as well, over you need to subtract that x minus y, so you just write a 2 minus 2.003, so based on the given value here, so you can see that how much the percentage of the error is. Okay, so you can calculate about when you just solve this, you get a 0.6667, so just like 4 significant places, and if you convert into the percentage, they give you the 66.67 percentage. Okay, now can you tell me now, is that the subtracting is error? So that means the subtracting of the number are nearly equal can be that unwanted inaccuracy. So you can prove that yes, it is. So even we just like we subtract is very closer to error out of this. All right. So it still is a lead to that error in that calculation. So this is what we causes in that propagations error. Okay, we call it the error propagations. So likewise, this is just small. When what happen if there is a different type of error? I mean, like large errors. So even the percentage will be even higher. Okay, so